Hello everyone. This is the fourth problem from RMO 2018. Let me read the problem statement first. Let E denote the set of 25 points Mn in the xy plane where Mn are natural numbers less than 5. Suppose the points of E are arbitrarily colored using two colors, red and blue. Show that there exist 4 points in the set S. So basically this, which means there are 4 points which are vertices of a square such that three of them have the same color. So this is a long case-based grind. So let us do it one by one. So first of all, let me draw a rough picture of the 25 points. These are the 25 points. Yeah. So what we are going to do is we are going to follow a systemic procedure of using pigeonhole principle to solve the problem. So first let us use the pigeonhole principle on these 5 points. So if we use the pigeonhole principle on these 5 points, there exist 3 points among these five which are of the same color. So these 5 points have 3 points which are of the same color. So choosing these 3 points, we can have two choices. Either the two colors are alternatingly arranged, which is like this, or there exist either this is the condition in the first row, or there exist. So what we are doing is we are assuming that red, red and blue are the two colors. So we are assuming that there are three reds here at least. So yeah, so there are three reds here. So either they are alternatingly arranged like this, or there exist two consecutive reds. Yeah. So first we are solving for two consecutive reds case. So let's do it. So first case is there are two consecutive reds in the first row. So if these two are red, then we don't know which row are they are in. But these two have to be blue. Otherwise, if one of them is red, then this small square, this small square has three points of the same color. And similarly, if we keep on proceeding, these two have to be red, these two have to be blue, and these two have to be red. So this is the configuration we get. If there are two reds of the same color, we don't know which row they are. So we will again proceed case by case. First, let's make a case that these are the first two rows. First two rows, which means that in the above schematic diagram, these two rows are like this. So going procedurally, suppose these are the first two rows, then notice that this or this cannot be read because this will form a square, this square, which have 3 points of the same color. So these two have to be blue, these two have to be blue, and similarly this also has to be blue. These two have to be red for the same reason. And going again one step. So these has to be blue. If this is red, then this square will form. So this has to be blue, this has to be blue, and this has to be blue, and this has to be red, this has to be red. What we are doing is we are doing a contradiction method. Like this is the worst case scenario. And continuing, this has to be red, this has to be red, and this has to be red because of the same reasons as mentioned earlier. This is blue and this is blue. So notice in our final configuration, these two rows were fixed and these three were forcefully generated so as to avoid a square. So nevertheless, even after avoiding every single square, these 4 points form a square which are the same color. So this case is done. So next case is this is first two rows. Next case is that this structure is already generated as for this structure, and we are now supposing that these are the second and third row. This is second, third row. Again, continuing in our same approach, these bottom two rows will be fixed as earlier. These bottom two rows will be fixed. And in a similar manner as before, the top row will also be fixed because say this is a red color, then these 3 points are forming a wrong triplet. So this has to be blue, this has to be blue, this has to be blue, this is red, and this is red. This only two rows were given, and we have forced every other entry. So again, these 4 points contradict the case. So we are done for the first two rows and second and third row. Note that third and fourth row is exactly same as second and third row, because what we can do, what we did, if these two, let me draw it again. So if this is the case, then in the third and fourth row, third, fourth row, then this is exactly the same case as this one by reversing the diagram. And similarly, fourth and fifth row is the same as fourth, fifth row, the same as this case by reversing the diagram. So basically what we have done is we are done for the case when two rows, two consecutive reds appear in the first row. Now the case that is left is that this is an alternate coloring set. Alternate coloring where no two reds are consecutive. So this is the configuration in the first row. And again proceeding out by our same procedure, because this is red, suppose this is the second row, then this third row, this has to be blue, because otherwise this and this will form a 3 points. And similarly we can generate this and this. And again going stepwise, this is the fifth row. So these two rows are generated. These rows are generated. Why? Because this is blue, so this cannot be blue. So again notice that just by considering first, third, and fifth row, this, and this are the same color. So we are done for this case also because they form a square having 3 points of the same color. So this case is done, and these two cases are also done. So we are done with the whole problem. Because by pigeonhole, the whole approach was by pigeonhole, we can select 3 points in the first row. And these 3 points must either lie in this order or 2 points have to be consecutive. By 2 points consecutive, we generated this and this row and this. And by alternate coloring segment, we generated this. So all cases are covered. So all have 3 points, have a square having 3 points of the same color. So we are done. Thanks.